section of the stoichiometry notes, we are going to be doing limiting reactants and theoretical yields. So with limiting reactants, in a normal situation, when you perform a chemical reaction, there will be multiple reactants. One of those reactants will be completely used up, and the others will be left over. And typically, you want to set it up to where your chemical reaction, the most expensive chemical, is the one that you completely use up, because the excess reactant is the one that's going to get dumped down the sink or put into the dump bucket underneath the vent hood or disposed of in some way. And you don't want to dispose of your expensive chemical. You want to dispose of the cheap one that you don't really care about. Finding the limiting reactant has a lot of steps, and it's really important to keep track of everything that you're doing so that you don't miss a limiting reactant question. So here is what looks like a very big example for limiting reactants, but it's actually broken down very similarly to how the AP exam breaks down their free response questions. So you can read through the question there. And on part A, it says, what is the limiting reactant? So to find out the limiting reactant, I'm going to take my amounts of each chemical, and I'm going to convert it to a product. And since part B is saying how many grams of water are formed, I'm going to go ahead and convert both of them to water. So starting with that, I have 255 grams of C8H18, and I'm going to convert that to water. Grams of water. Wait. Now we just stop at moles of water. That'll be plenty. So if you remember, this had a molar mass of 114 grams per mole. And then for every 2 moles of octane, I'm going to get 18 moles of water. And so this works out, 255 times 18 divided by 114 times 2 gives me 20.1 moles of water. That's if we use all the octane. If we use all 1,510 grams of the oxygen, let's see how much water we could produce. So 32 grams of oxygen. The reason I'm using 32 now and not 16 is because I'm actually dealing with elemental oxygen, which is a diatomic molecule. Before, I was just dealing with the oxygen that was contained in some compound, so I didn't have to worry about it being diatomic. So this is in every 1 mole of pure oxygen, and for every 25 moles of pure oxygen, we are going to be getting 18 moles of water. And I plug this into my nifty calculator. And I get 34.0. So now to determine the limiting reactant, I got to look and say, okay, who's going to produce less? Because that's the one I'm going to run out of first. And so since this produces less water, that means octane is my limiting reactant. So my limiting reactant is C8H18. Now they want to know how many grams of water are formed. Well, if this is how many moles of water are formed, to figure out grams, all I have to do, one step further, for every mole of water, I'm going to have 18.02 grams. So 20.1 times 18.02 gives me 362 grams of water. So that goes here. 362 grams of water. How many grams of the excess reactant is consumed? Well, to figure that out, I have to figure out how many grams of the excess reactant is going to be used up in this amount of octane right here. So I'm going to start writing up here because I'm getting a little low on room. So 255 grams of octane, and I'm going to convert that to grams of my other reactant, my excess reactant, the oxygen. So this again, molar mass of 114 to every 1 mole. And for every 2 moles of octane, I'm going to need 25 moles of oxygen. And each mole of oxygen has a mass of 32 grams. Plugging this in, 255 times 25 times 32 divided by 114 times 2 gives me 895 grams of oxygen that I use. But the question said how many grams, oh, that is what the question asked. How many grams of excess reactant is consumed? 895. If it had asked me how many was left over, then of course I would subtract. Oh, right there. How many grams of excess reactant is left unreacted? Well, I had 1,510 grams of oxygen. I used 895, so I just simply need to subtract. So 1,510 grams minus 895 grams, and that gives me 615 grams of unreacted oxygen. So there's that one. Theoretical versus actual yield. The theoretical yield is what you should get in a reaction, but inevitably reactions don't go exactly how they should, so we have the actual yield, which is what you perform, what you get in the lab. And I know I put almost always. Sometimes you have issues where you don't react something completely, and so you don't form all the product that you should, and you still have a little bit left over of the reactant, so it appears that the actual yield is more than the theoretical yield, but it's just not possible. So the percent yield is the comparison of theoretical to actual. You basically take actual divided by theoretical, and again, multiply by 100. Got to write that 100. So in the previous example, the theoretical yield of water should have been 362 grams, theoretical, but we only got 312 grams. Hey, there's the bell for the next class period. Isn't that great? To figure out the percentage, you multiply this by 100, take those two and divide them through, and you end up with an 86.2% yield, which is not too shabby. Okay, if you guys have any questions, you can email me on here, or if you're actually one of my children, you can email me through the school or just come talk to me in the morning, and I will see y'all then. Later.